Everybody, now we're going to talk about cell potential, which is the voltage that a cell puts out. A lot of times in batteries, you know how many volts your battery has. Well, that potential can be easily calculated and can be easily determined. Okay, and so cell potential is how much force that is causing the electrons to move. And so this is like a chemical force that's pushing the electrons off of an atom. Okay, and sometimes this is called EMF, electromotive force. And it's measured in volts. Okay, now we're always going to deal with standard potentials in here. Okay, standard potentials means that we're dealing with reactants and products that are in what we call the standard state. Okay, so oxygen, O2 would be a gas, iron would be a solid, that sort of thing. Okay, if it's an aqueous solution, aqueous solutions always have concentration of 1 molar. If it's a gas, it's going to be a pressure of 1 atmosphere, and you can read all of these things. Okay. This video is not going to deal with non-standard conditions. We're not going to get into the Nernst equation in this case. Okay, and so I think all of this boils down to the fact that there has to be a basis, and so we use hydrogen's reduction potential in order to determine the basis, and that is equal to 0 volts. So if there's more electromotive force, that means that it's a positive voltage. If there's less electromotive force, that's a negative voltage. I want to say that it's an arbitrary designation, but it's not really. But we're just not going to get into why hydrogen is the basis. Okay, just know that hydrogen, when hydrogen is being reduced, that is the basis for what for the chart, okay, or for the standard reduction potentials. Okay, so the formula for standard reduction potentials is fairly straightforward, or calculating the cell potential. Okay, and so here's the thing. This is standard cell potential, and I always kind of step through why the formula looks, or why the symbol looks so funny. This is potential. E is potential, and it's E because it's kind of like an energy, but that's what we're talking about. And this is standard because, again, we're not dealing with non-standard conditions. And then this is for what thing, and this is the cell. Now, every cell, voltaic cell, galvanic cell, whatever you want to call it, is made up of 2 parts. There's the cathode and the anode. Okay, and so this is how we do this. This is how we sort of do this math, is we find the reaction and we find the cathode, and what happens at the cathode reduction, red cat. So we find the reduction, and then we find the anode reaction on this table of standard reduction potentials. Now this is a big long table here, and I scrunched it all up. Okay, you can probably guess that this is the hydrogen. Okay, but let's step through a problem, and I will call up an actual table of standard reduction potentials so that we can see how to use it. And I'll do a little math. So here's the same where we have silver. Silver is undergoing one of the half reactions, and copper is undergoing the other. So silver is losing electrons. It's going from a plus. So this is being reduced. It's gaining electrons. I don't know. Every once in a while, I get all crazy. But this is gaining electrons because the charge is going down. Electrons are negative. You're adding a negative, so the charge is going down. Copper is oxidized in this case. So that's something that we can figure out. Now, just a reminder is that we want the cathode minus the anode. We don't necessarily want reduction oxidation. So the Barnard principle, there's a red cat and an ox. So we're going to want to find the the cell potential by finding the cathode, the potential of the cathode, or the thing that's being reduced, minus the cell potential of the anode. Okay. So, the way to do this, well, so I went to the internet and I found this sheet that's got cell potential, or, okay, reduction potentials, if we look there. Okay, so it's got reduction potentials for various elements. Okay, so keep in mind that these are what we call reduction potentials. So I'm going to go down and I'm going to find the right copper and the right silver. So if we look here, this is what makes this so much fun, is we have 3 different coppers. Well, which copper is the one that we're interested in? Are we interested in the copper plus going to copper solid, copper 2 plus going to copper solid, or copper 2 plus gaining only 1 electron and going to copper 1 plus? Okay, so we're going from, okay, copper to copper 2 plus. Now, this is the oxidation half reaction. So let's address this. Notice that this is the half reaction for this is copper reacts to form copper 2 plus 2 electrons. Okay. Well, when we look at this, that is almost the same as this reaction, but notice it's just backward. Okay. Now that's okay, because what is the reaction here? What kind of potentials are these? These are standard reduction potentials, and this was the thing that was being oxidized. And so this is the one we want. So it's 0.34 is the voltage. Okay. So 0.34 here. Which one is it? This one. Okay. So this is 0.34 volts. Okay. So now we look at silver. This is the thing that is actually being reduced. So we don't have to do as much interpretation here. Okay. So silver, oh look, silver is up here. It's at 80 volts, and it's written the same way, so we don't have to worry about where it is. And there's only one silver reaction. Okay, so it's 0.8 volts. Okay, so this is the cell potential equals 0.80 volts minus 0.34 volts. Okay, and so let me just pull this up so that you guys can see this. Okay, and yeah, electrochem is equal to 0. Okay, so we get 0.80 minus 0.34, and when we do that, we get a cell potential of 0.46 volts. Okay, so let's get rid of the calculator and let's just move on to some kind of general rules. Okay, so the idea is that the stronger oxidizing agents have the more positive reduction potential. Okay, so remember that the thing that is being reduced is the oxidizing agent. So that means that the more positive it is, the stronger it is. So when we go to our thing here, all of these guys with positive, these are the strongest oxidizing agents. And so, not to insult your intelligence, but just to say here, the opposite is also true, is that when you have more negative reduction potentials, okay, that it's the more, it's the thing that is the stronger reducing agent. Now, here's an interesting little tidbit that may help you out, especially if you're ever going to talk about spontaneity. Okay, there's something called the northwest-southeast rule. Okay, and you can write it down here, but let me pull up the periodic table. Okay, so the idea is that with the northwest-southeast rule, okay, if you have a substance up here in the northwest, anything that's below it and over here will definitely react. Okay, so this is southeast of the northwest, and so that gives the reaction a product favored thing. It's going to be product favored. Okay? So that's how that's one of the ways that we can determine if something, that's like a shortcut for determining if a reaction is going to be spontaneous. It's called the northwest southeast rule. Okay, and that's always going to be the case. You're only limited now by the type, by all the reactions that are in your on your list of reduction potentials. Okay, just be careful, because sometimes you'll be given a list and that's not going to have reduction potentials on it. I went through that when I was searching this. Most tables are reduction potentials, but not necessarily this one. Okay, so anyways, that's how you calculate cell potential. Have a great day.